All right, y'all, we'll try take two. So today we're going to be talking about differential equations again. This is a continuation of 6.2 and 6.3, but kind of some of the other situations, some more word problem-esque that we use with differential equations. And we're going to start out by talking about what we call the proportionality constant. I really suck at saying the word proportional. But anyways, so write and solve the differential equation that models the verbal statement. When we set up this differential equation, we account for the proportion. So you're always going to see this word proportional, but we account for that word with the constant k. So I know we already have the constant c, our constant of integration. K is our proportionality constant. So these differential equations are known as general solutions for exponential growth and decay equations. So growth and decay, you should recognize it from exponential functions with algebra 2 and with pre-calculus. You know, your e to the something, your 2 or 3 or 4 to the something. Those are your exponential functions. And you had growth and decay. Like if it was 1 plus a percentage or 1 minus a percentage, it was growing or decaying by a certain amount. This is what differential equations are used for. And calculus is really the behind to those equations. Those equations were found originally using calculus. So we're going to kind of do the same thing. So we're doing like the groundwork for those exponential functions. Well, let's get into it. So number 11, the rate of change of y with respect to t is proportional to y. So let's read that first part. The rate of change of y with respect to t. We have experience with this from back with related rates. We would represent that by dy dt, the rate of change of y with respect to t. Then it is proportional to y. So we say it is equal to our proportionality constant k. So k, anytime we see that proportional, we're going to use our constant k. And then we always multiply the proportionality constant by whatever it says it's proportional to. So it's proportional to y. So we just say k times y, just like that. Okay. Now this is a differential equation. This is just writing it. So this is the first part. Okay. The follow-up, and this question doesn't tell us to do this, but I do want to show you this process. But the follow-up to just writing a differential equation using a proportionality constant is to actually solve that differential equation. So we're going to solve it real quick. So separate, separate, integrate, integrate. You might notice that we're using dt instead of dx. That's okay. Works the same way. So I can divide that y over, and on the other side, I'd get k dt. I'll write my t first before I write my t. Okay, so a couple things. First thing, notice k is a constant. It's not a variable. K is a constant, so keep that in mind. So this is a constant times dt. Number two, I only divide over the y. You could technically move k over to the other side, but it doesn't really make any sense. It doesn't make your life any easier, and realistically, you'd probably end up multiplying it to the other side anyways if you wanted to get y by itself. So it really makes more sense to leave k always over on the right side of the equation. So from here, I've separated both sides, y's with y's, t's with t, and my proportionality constant k, but that's just a constant. That's okay. So integrating both sides, dy over y, that gives me the natural log of the absolute value of y. On the right side, the integral of k, which is a constant, like 1, 2, 7, natural log of 4, something like that. So the integral of k is just k t. Okay? Some amount of t, some constant times t. And then we add in our constant of integration. So we actually have two constants, two unknowns here. We have k and we have c. C is the constant of integration. K is our proportionality constant. Okay? Two different constants, two different variables, but they're actually constants. I know it's weird. Just try to get used to it. So, of course, we could leave it like this. If we wanted to solve it out for y, though, we can take a base of e to both sides. So that's going to get those e's to cancel out. So we get just y is equal to e to the kt times e to the c. And of course, we know e to the c is really just big C, and then of course that e to the kt. So this is really, this is our final answer. This is our solved out for y. Okay. Notice we have two constants. So if I wanted to solve this function all the way out, if I wanted to get an actual general solution, remember right now this is what we call this is a general solution. If I wanted to find a particular solution, I would not just have to give you one initial condition to solve for C. I'd have to actually give you two initial conditions, one to solve for C and one in addition to solve for k. And you'll see this a little bit when you get to that Newton's Law minor grade. You'll see that you're given two sets of data points so that you can solve for the two different constants you have. Okay, let's keep working. I've talked enough on number 1. So let's look at, or number 11. Okay, let's look at number 12. The rate of change of p with respect to t is proportional to 10 minus t. So rate of change of p with respect to t, we would just write that as dp over dt. And then it's proportional to, so proportional constant k, and then 10 minus t. So since I want to make sure I multiply all of 10 minus t by the k, I want to do it in parentheses. So that entire 10 minus t is proportional to dB dt. So anytime you have more than just a single variable, make sure you put it in parentheses before you multiply by that constant k. Okay, then same thing, this is my differential equation. This is all this question is asking you to do. It's just to write it. But if I wanted to solve it out, I could separate, integrate. So we'd get dp, because I don't have any other p's, so I'm just going to leave dp over on the left side by itself. I can multiply that dt over, and I can distribute that k. So 10k minus kt, and then I'll, of course, multiply by dt. Then once I've separated, I can integrate both sides. On the left side, integral of dp is just p, because it's technically 1 dp. Over on the right side, 10k becomes 10kt, okay, because I'm adding in 10 and k are both constants. So I just have one big multiplied constant right there. And then minus kt squared over 2. And then, of course, adding in that constant of integration. And p is already solved on this one, so I don't have to do any extra grunt work. That would just be our final answer on 12. Okay, so two slightly different ways to see these. You will see lots of different of these proportionality constant k's. They are a favorite on the AP exam. They typically show up as a multiple choice question, but they're also relatively easy in terms of you just multiply whatever it tells you to multiply by k. You just got to remember it. Okay, so anytime you see that word proportional, okay, anytime you see proportional, proportional means our constant k. So proportional means k. Don't forget it. All right, let's look at 13. 13 isn't anything too special, but it is kind of a word problem. This is really set up like an actual FRQ that you would see on differential equations. And differential equations, when we get to them, this whole chapter is a short chapter, but you're also kind of learning a whole FRQ. Every time you get differential equations on the AP exam, it's typically a whole FRQ on its own. So by the end of this chapter, we're going to have a whole new set of FRQs we can do with differential equations. So 13, let f be a function with f of 1 is equal to 3. So that's an initial condition. 1 being the x value, 3 being the y value, such that for all points x comma y on the graph of f, the slope is given by y over x squared. So remember, we've learned this before in calculus, the slope is represented by what in calculus? It is the derivative. So y over x squared is our function for the derivative. It is dy over dx. Okay, they're not always going to make things really easy and say this is the derivative and this is the integral. Sometimes they're going to use some of our other vocabulary to explain those terms to you. And you're going to have to know calculus a bit to be like, oh, slope means derivative. Nice and easy. All right, so part A, we want to find the slope of the graph of f at the point where x equals 1. Well, Mr. Darbone, you just told me that's the slope. Well, that's the equation for slope. Remember, derivative is our slope generator. I want to find slope specifically at the point where x equals 1, and my derivative happens to have both y and x in it, so I'm going to plug both my x value of 1 and my y value of 3, which I got from f of 1 equals 3, into my derivative to get my slope. So dy over dx, is equal to 3 over 1 squared, which is just equal to 3. So if you got that on an AP exam, I really hope that's the easiest point you could ever get. Okay, and it shows up. Don't think that question doesn't show up on the AP exam. It shows up. This is a real FRQ that this is pulled from. Okay, part B. Find f of x by solving the separable differential equation dy over dx is equal to y over x squared with the initial condition f of 1 equals 3. Okay, so now this is our whole chapter, differential equations. Separate, separate, integrate, integrate. So let's go ahead and start off. So we get dy over y is equal to dx over x squared. Integrate both sides. Over on the left side, dy over y just becomes the natural log of the absolute value of y. Over on the right side, I can move that up first. This becomes x to the negative 2 dx. So I get the natural log of the absolute value of y is equal to x to the negative first divided by negative 1. And then, of course, tack on that constant of integration plus c. So before I even plug in my initial condition, the natural log of y is equal to negative 1 over x plus c. Okay, so now, remember, I always want to try and plug in initial condition before I solve anything out. So I'm going to go ahead and plug that initial condition in now. So x is 1, y is 3. So we get the natural log of 3 is equal to negative 1 over 1 plus c. So that means the natural log of 3 is equal to negative 1 plus c, which means the natural log of 3 plus 1 is equal to c. Now that is a gross constant of integration, but you're going to see it's going to get a little prettier in the end. So let's go ahead and plug it in. So we get the natural log of absolute value of y is equal to negative 1 over x plus natural log of 3 plus 1. Okay. From here, I can go ahead and take a base of e on both sides because I want to get y by itself. Remember, we do this all the time in chapter 6. So on the left side, it cancels out. We get just y. On the right side, we get e negative 1 over x. That's not going to cancel out. Plus natural log of 3. Okay, so e and natural log of 3 I could get to cancel out. Plus 1 I can't get to cancel out. So I'm going to leave this as negative 1 over x plus 1 times e to the natural log of 3. So notice how I kind of pick and chose what I wanted to split up into separate bases of e. So negative 1 over x and 1, both of them are not going to get that base of e to cancel out. So I'm just leaving them as e to the negative 1 over x plus 1 because that's all going to stay like that. I can't get anything to cancel out. E to the natural log of 3, that's really e to the c, which is really our big C. So then we would get e to the natural log of 3. E and natural log are going to cancel out. And we get y is equal to 3 e to the negative 1 over x plus 1. And there you go. So that is a little more involved than maybe all of your differential equations, but that really is a true FRQ for chapter 6. That's a differential equation free response question. Notice how probably a little more challenging than most of the ones that we saw in the notes. But not anything too terrible, not anything we can't handle. Okay. The one thing that I do want you to see, remember I told y'all that you don't have to solve for y in these unless they tell you. So the spot where they told you in this problem was right here. Find f of x. So if they say find f of x, find y equals, find f of x is equal to y, find y is equal to f of x, any sort of they're specifying that you have to find f of x, y, whatever, then you need to solve it for y because they want you to find that. Okay, so y is the same as f of x. You don't have to change it back into f of x at the end. They understand that if you put y, you mean f of x. But anytime you see that written down, that means you have to solve it for y. All right, let's talk about 14. 14 isn't an FRQ, but it is a question you'll see. It shows up as a multiple choice question a lot. It's not too terrible. It just kind of has an extra step tacked on. So if dy over dx is equal to 2y squared, and if y is equal to negative 1 when x is equal to 1, then when x is equal to 2, what does y equal? So this is kind of practicing that step of giving you double initial conditions. So they've given you an initial condition when x is 1, y is negative 1. And then they've given you an x value and asking you to find the y value. So all we're going to do is we're going to separate, integrate. We're going to plug in our initial condition and find our particular solution. And then we're going to plug 2 in to our equation to solve for y, just like we would normally in any other day in math class. We're going to plug a number in to get another variable out. Okay. So if dy over dx equals 2y squared, then we can go ahead and separate, integrate. So dy over y squared is equal to 2dx. Integrate both sides. Dy over y squared, same thing we did in the last problem. We can move that up to make it y to the negative 2 dy is equal to 2x plus c. Integrate that. That becomes y to the negative first over negative 1 is equal to 2x plus c, which is just negative 1 over y equals 2x plus c. Now, as always, we like to plug in first before we do anything else to solve for y. So let's go ahead and plug in for our value for c. So y is negative 1, x is 1. So negative 1 over negative 1 is equal to 2 times 1 plus c. So 1 is equal to 2 plus c, which means negative 1 is equal to c. So for our equation, we get negative 1 over y is equal to 2x minus 1. And I really don't need to solve for y. You could solve for y. It's a little involved. I'd have to multiply y over and divide it. It's kind of a mess. Instead, I can just plug in 2 right here, and I can solve for y in the end. So this is my particular solution. So I have my function of y. Okay, now I'm going to plug in 2 to solve for the value of y. So when x equals 2, what would the value of y be? So I can go ahead and plug that x value in. So negative 1 over y is equal to, that looks like 2 and 2, is equal to 2 times 2 minus 1. So negative 1 over y is equal to 4 minus 1. So negative 1 over y is equal to 3. Multiply that y over, we get negative 1 is equal to 3y. Divide that 3 back over, and we get negative 1 divided by 3, or negative 1/3, is equal to y. So anytime you get a problem like this, y'all, your final answer should be a value of y. So just to kind of recap 14, because it is a little bit different. So separate, integrate like normal. Plug in your initial condition like normal. But then once you have that particular solution, the extra step is you then plug in another x value to solve for the y value. So y'all, that is the end of our 6263 differential equation notes. Just kind of some extra little problems and running through a full FRQ talking about that proportionality constant. So you should be able to do all of the practice now, and you should be able to get started on working through those 4 Newton's law minor grade questions. It's only 4 questions, so it's not a lot. You have all of 2 weeks to work on it, maybe even some extra, just kind of depending on how school goes. But that is differential equations, y'all. Send me any questions you might have.